All right, we're going to take a look at worksheet number 24 here that we had for homework last night. We're going to go over 4 questions, 2, 3, 10, and 14. A couple of these questions relate directly to what we talked about yesterday. Okay, the idea of radioactivity, the idea of transmutation, the conversion of one element to the other. They all relate to transmutation, but there's a couple of these questions that we're going to go over that aren't, strictly speaking, radioactivity, that aren't those natural processes. That natural process whereby the nucleus spontaneously splits up. We'll talk about that in a little bit more detail in a second here. Number 2. 2 says we start with 22286. Doesn't even say what that is. Is that radium, I think, Ra? Or Rn, radon? Radon? Okay, so it should say, no, let's write it over here. It should have said that, although it doesn't really affect how we do the question. We know how to do the question whether we see the symbol there or not. Okay, we gotta make sure that all the mass numbers add up, all the atomic numbers add up on the left side and the right side. So let's do the mass number first. On the left side, we got 222. On the right side, we gotta have 222 as well. 4 plus 218 gives me 222. 86 on the left side, 2 plus 84 gives me 86. What's atomic number 84? Polonium? Is that right? Anything else that's produced there? Like a neutrino or an antineutrino? Neutrinos and antineutrinos are only produced with beta plus and beta negative decay, right? If you got alpha decay, it is what it is. The alpha particle is produced. This ionizing radiation that is this alpha particle is produced, as well as some daughter nucleus that's almost the same size as the parent nucleus that we started with, but nothing else, right? That's the end of the question. Number 3. Says lead-214. It decays into bismuth-214. And bismuth has an atomic number of 83. Again, we got to make sure that the mass numbers add up. They already do. 214 plus 0 is going to give me 214. But the atomic numbers don't add up. We get 82 on the left-hand side. We get 83 on the right-hand side. How do we turn 83 into 82? 83 plus what equals 82? 1? Is that right? How about negative 1? 83 plus negative 1 gives me 82. What kind of particle is that? What else could we call it besides a beta particle? It's exactly the same thing, exactly identical to an, there's your hint right there, it's an electron, right? What else is produced there? Go ahead. Yeah. One of those negative U thingies. We call it an anti-neutrino. Yeah. If it was beta plus, right? Let's say that wasn't beta minus decay like it is. Let's say it was beta plus, then it wouldn't be an anti-neutrino produced. It would be a neutrino produced. Right? We got to always balance out the mass number and the atomic number. When we got beta plus or beta minus, we also have this neutrino or this anti-neutrino that's produced. And we know that. Go back 80 years ago, almost 80 years ago. Wolfgang Pauli in the year 1930, who hypothesized the existence of those neutrinos and antineutrinos to account for this missing energy. Okay? We write out the equation just like this. Okay, that's great. We're balancing out everything, but we're missing some energy, which doesn't really show up in the equation, but still a physical reality that we're missing that energy. So we got to have that antineutrino to account for that missing energy. All right. Number 10. Number 10 is what we call an artificial transmutation equation. The way that we balance this is exactly the same as the way that we balanced the first 2 questions that we did here today, except that the first 2 questions were natural radioactivity questions. Alpha decay, then beta negative decay. This isn't. This isn't alpha decay or beta decay. This is, look, we take beryllium, we bombard it with a hydrogen nucleus here, and then we see what happens. I used an analogy this morning. I'll use it with you guys as well. You got this big iceberg in the North Atlantic. It's like it wants to break apart. It's like a chunk of ice wants to break off, but it's not. So what do you got to do in order to make the chunk of ice break off? You got to ram it with a big ship. So when the Titanic hits the iceberg, what happens to the iceberg? Well, a little chunk of the iceberg falls off. Okay, that's what we're doing here. This hydrogen is the Titanic. The beryllium is the iceberg. We're ramming the iceberg with the Titanic. And then what happens? Well, it splits up a little bit, right? The iceberg breaks apart now because we've just rammed it with the Titanic. Well, it breaks apart into lithium-6 plus something else. Let's write this out a little bit bigger so we can see it a little bit bigger as we're calculating the numbers. So our big iceberg smashed into by the Titanic breaks up into this smaller iceberg plus what else? Well, on the left-hand side, 9 and 1 make 10, 4 and 1 make 5. On the right-hand side, 6 and 4 make 10, 3 and 2 make 5. What has an atomic number of 2? Helium. It's a different isotope of helium than we're used to seeing. All right, 3 there, 4. Should it be, yeah, it should be 4, right? Yeah, that's right. It's not a different isotope of helium that we're used to seeing. That's the most common one, right? Helium-4. Radioactivity? No, it's not radioactivity. Okay, we're making it happen. Okay, if the iceberg breaks apart on its own, that's analogous to radioactivity. If we have to smash the Titanic into the iceberg to make it break apart, then that's not natural radioactivity. We're forcing that to happen. That's an artificial transmutation reaction. All right, and finally we have number 14, which is also an artificial transmutation equation, because again, we're bombarding the iceberg with the ship. We're hitting the iceberg with the ship. The nitrogen-14 isn't breaking apart on its own, so we smash something into it, this alpha particle, and then it decays into oxygen-17 plus something else. This one's a little bit confusing, though. You look at this and say, oh, well, it's alpha decay, right? Because there's an alpha particle involved. No, it's not. It's not alpha decay any more than smashing hydrogen into beryllium was alpha decay. We're not producing an alpha particle here. We're taking an alpha particle that we already had and smashing it into the iceberg, or smashing it into the nitrogen-14 here. So what is this going to look like here? We got our nitrogen-14, we got our alpha particle that we're smashing into it, well, bombarding the nitrogen with, produces oxygen-17 plus something else. Well, 14 plus 4 is equal to 18, 7 plus 2 is equal to 9, 17 plus 1 is equal to 18, 8 plus 1 is equal to 9. What do you got here? 1, 1. Oh, that's a beta particle, isn't it? Beta plus? It's not beta plus. Beta plus was 0, 1. Okay, that's not 0, 1. 1, 1, you could write it in two ways. Hydrogen. Atomic number 1 is hydrogen. If you're ever in doubt, look at your periodic table. Look for the atomic number on the periodic table. Anybody know another way that we could have written that, though? Remember, we've written 0 minus 1 beta, same thing as 0 minus 1 electron, right? 1, 1 hydrogen is the same thing as 1, 1, could have been a proton, right? Because you got one proton there. A hydrogen nucleus is just a proton, right? At least that isotope of hydrogen. Good? Got it? Go ahead. They can be produced, I wouldn't want to say in every scenario. In fact, some of these might not even be energetically possible scenarios because I've made up some of those questions in terms of the artificial transmutation. But gamma rays can be produced in a number of different reactions as a result of that excited nucleus. So I don't want to say specifically for anything that you see up here, because some of these reactions might not even be energetically possible, but it can be. Okay. All right, let's take a look at one multiple choice question. We're not going to have you submit this, but I will have you do it yourself at your desk, and then we'll take a look at it in about 60 seconds after you've had that chance. Okay, this question says, some smoke detectors use the radioactive source americium-243 to ionize air between two electric plates in a detection chamber. You got a battery that's causing a current. When smoke enters, they neutralize these ionized air molecules, which decreases the current, triggers an alarm. There's a lot of stuff in here that we don't need to know the first thing about, right? What do we need to know? Well, we need to know that we're starting with americium-243. We don't even know the atomic number, but yet we're given all this other stuff that we don't really need to know. What is the atomic number, by the way, for americium? Let's look it up on our periodic table if somebody doesn't have it already. 95, thank you. It says, if the air is ionized by alpha particles produced by americium-243, what byproduct would you expect to find here? So we've got these alpha particles that are produced by americium-243. The alpha particles are going to appear on the right-hand side as a product because they're produced by this decay of americium-243. What else we got? 243 plus, 4 plus 239 gives me 243. 2 plus 93 gives me 95. Atomic number 93 is what? It doesn't really matter here because in the end, there's only one answer that has a mass number of 239, right? Which is D. So in the end, we probably want to take a look at this just to make sure atomic number 93 is that element, okay, just as a backup. But in the end, we've already got our answer here. What is this, by the way, guys? What symbol is this? Neptunium, NP? And is that atomic number 93? Okay. Good. Good there? All right. Today we're going to spend a little bit of time not so much on what the reaction looks like, but rather we're going to spend the time on how quickly the reaction takes place. In order to do that, we have to define a new term called half-life. You've heard of this before, right? Don't necessarily know what it means. If you've taken math class, Math 30, you might actually know what half-life is because you probably talked about it very briefly in math class before as part of a exponential growth or exponential decay. The half-life of a particular element, a particular radioactive element, is the time that it takes statistically for half of a radioactive sample to decay into something else. So when I say that, there's a couple things that I want to clarify. One, that word statistically. What does that mean? The time that it takes statistically for half of it to decay. Statistically. Well, the reality is we don't know exactly how quickly something's going to decay. If it's radioactive, it decays spontaneously and naturally. It's what we call a quantum process, actually. We don't know at what rate it's going to decay, but we can make predictions as to how quickly not one nucleus will decay. We can make predictions as to how quickly a group of nuclei will decay based on the statistics of what it's done in the past. So what I'm saying is this. You got 1,000 nuclei. We know on average that 1,000 nuclei will decay this quickly. We may be off a little bit in the exact time in which it decays. We're basing our prediction solely on what 1,000 nuclei have done in the past. But if you've got a lot of nuclei, chances are it's going to do exactly what it's done, or pretty much what it's done in the past. Having said that, if you've got a small number of nuclei, all bets are off. The predictions that we make are pretty much useless, pretty much worthless. It's kind of like saying this. You got a coin. And on that coin, on the back of the coin, is heads. Let's say you get two of them. They're both heads. We got them sitting on a desk, they're both heads. We'll say that when it says heads, it's radioactive. It's still active. It's still ready to decay when it says heads. When it has tails, it doesn't mean that it's gone and nothing's there. You still have a coin there, but it's decayed into something else. It's decayed into tails. All right, so we flip these two coins. What would you predict is going to happen when you flip these two coins? What's your prediction? What are you going to end up with? Both tails? So you're going to predict that both of them are going to decay here then into tails. Well, statistically, if you flip two coins, one of them is going to end up heads and one of them is going to end up tails. But when you're only flipping two, it's pretty hard to base a bet on that prediction, right? Because when you're only dealing with two, statistics don't always work out the way they're supposed to. You might very well end up with two heads. In other words, you get two radioactive elements, you flip them both. After you flip them both, they're still radioactive. Or maybe you flip them both and neither one of them are heads. Neither one of them are radioactive. When you're dealing with a small sample size with coins, it's difficult to make predictions as to what's going to happen. When you're dealing with a small sample size for nuclear elements, it's difficult to predict exactly what's going to happen. But if we introduce 998 more coins, 1,000 heads, 1,000 coins, and we flip 1,000 coins, then odds are we're going to end up pretty much with 500 heads and 500 tails. We could be off a little bit, but our prediction has a pretty darn good chance of being pretty close. Does that make sense? The bigger the sample size, the more likely our prediction is going to be correct. All right. When we take a large group of radioactive elements, we know based on past performance approximately how long it's going to take for half of them to decay. We call that the half-life. Now, it's not certain. We never know for certain how long it's going to take them to decay. But if we have enough of them, we can use probability statistics to make a good prediction as to how long it's going to take to decay. Half of them will decay in this much time, the half-life, on average, statistically at least. All right, so let's say you start off with 1,000 nuclei. They're all radioactive. The half-life is 5 years. How many of those radioactive nuclei do you have left after 5 years? 5 years have gone by. You started off with 1,000 heads. How many heads do you got left after 5 years? 500. Right? Half of it has decayed on average in one half-life. Where's the other 500? Well, they're not gone. They've just decayed into something else. So we had 1,000 radioactive nuclei. Now we have 500 radioactive nuclei and 500 of something else. That's after one half-life. After two half-lives, what do you got left now? What do we have left after two half-lives? 0? Have they all decayed? Okay, so you're saying you got 250 left, which would mean we still have 1,000 nuclei, but 750 of them aren't radioactive now, right? They've decayed into something else. Anybody say 0? 250 is right. At the beginning of the first half-life, we had 1,000. After that, half of them will be gone. At the beginning of the second half-life, we had 500. At the end of that, half of those will be gone, on average. So at the end of the first half-life, we've got 500. At the end of the second half-life, we've got 250. And then so on and so on. We end up with, after 3 half-lives, 125 left. And then, wait a second. What do we go to next? 62 and a half? Can you have 62 and a half nuclei? No. Remember, we're making predictions based on statistics. So we're not claiming these numbers to be exact, perfect numbers. We're claiming these to be averages. On average, this is what you're going to have left after 1 half-life, or 2, or 3, or 4 half-lives. We can't have 62 and a half nuclei, but we can, on average, have 62 and a half nuclei. Sometimes maybe a little bit more, sometimes maybe a little bit less. Okay, let's look at a little bit of mathematics here. There's 2 equations that you're going to see here. One that doesn't appear on our data sheet, but really comes from something we did earlier this year. The other one that does appear on our data sheet, a little bit more complicated, but for most of you, you've probably seen it in math class already. First one, N, which is going to stand for the number of half-lives. If the half-life is 5 years and 15 years have gone by, little n wouldn't be 5 or 15. Little n would be 3, the number of half-lives. We're going to find that by taking the total time and divide it by the time for 1 half-life. That equation is not on our data sheet, but if you think about it, it's exactly what I've told you a number of times before when you're trying to find a number of something. A number of electrons, total charge by the charge of 1 electron. Number of photons, total energy divided by the energy of 1 photon. Number of half-lives, total time divided by the time for 1 half-life. N is equal to T over T1 half. And finally, the last equation. N is equal to N subscript 0 times 1 half to the little n. How many people recognize this equation from math class? Question? No, that's just a little subscript, yeah. So that's the symbol for half-life. It's not T times 0.5. It's just, we could have called it TX if we wanted to. The subscript is 0.5. It's 1 half, just indicating it's a half-life. I guess. Yeah. Where have you seen that equation in math class? In what context? Where have you seen that equation or something that's almost like that equation before in math class? Okay, so exponential growth or exponential decay? Okay. No, that's fine. That's fine. This is exponential decay, right? So you would use probably in math class a slightly more general form of the equation than we're using, but it's essentially the same thing here. We're saying N, which is the final amount, what we end up with, right? That's what it would have been in math class, the final amount. It might have been the final amount of money that your car was worth. The final amount is equal to the initial amount, the starting amount, times 1 half to the little n, which we already established is the number of half-lives. What units do we use? Well, there is no units for number of half-lives. It's just a number. What units do we use for n and n0? Well, I'll tell you what. It doesn't really matter as long as you're consistent. They both indicate an amount. Amount can be grams, kilograms. It can just be a number. It can be a percent. It can be moles. It can be anything that indicates an amount. As long as you're consistent with initial and final. Doesn't really matter. If you got something that means amount, go with it, run with it. All right. We're going to use the laws of probability in these 2 equations to make predictions now as to what's going to happen to these large groups of radioactive elements. Remember, they are just predictions. We can never know for sure what happens, how quickly these reactions take place until after they've taken place. Also know this, what I'm teaching you here today, we say that we can never know until after it's taken place. We're making predictions, nothing certain until after the reaction's taken place. I'm not trying to simplify this for you. I'm not trying to dummy this down for you because you're only 17 or 18 years old. There's nobody that can make predictions better than we're going to make predictions here today. It doesn't matter if you have a PhD in physics. You still can't predict exactly what's going to happen until after it's already happened. This is a natural, random process. It doesn't matter how smart you are. You don't know exactly what's going to happen with a random process until after it's already happened. Okay, so we're not dumbing it down for you. You guys are as smart as a PhD physicist here today, at least in this aspect of physics. Okay, two example questions here. Here's the first one. Radon-222 has a half-life of 3.82 days. What percent of the sample of this isotope remains after 2 weeks? How much remains after 2 weeks? We're going to say the half-life is 3.82 days. How much remains after 2 weeks? Well, the total time is 2 weeks, but we want to be in the same units, so let's make that 14 days. We could have made the 3.82 days into weeks, but it's easier to turn the weeks into days, I think. So that's what we'll go with. We want to know how much remains. We want to know N. Is there anything else we have here? Anything else that's given to us here? The final amount we're looking for. Do we know what we start with? The initial amount? Nick? Good. If we're dealing with a percent, generally the initial amount will be 100. Now, there are exceptions to that, but when those exceptions occur, it'll be pretty clear. Right? It'll essentially tell you the initial amount is, 58% of what we had last year. So we'd say Ni or N0 in that case would be 58%, right? But usually N0 would be 100% if you're dealing with the amount as a percent. Okay, let's find N here now. Got to find a little n by saying T over T1 half. So it's going to be 14 divided by 3.82. We got 3.665. No units there, right? Just a number of half-lives. We're going to do this on our calculator because we haven't done any calculation like this yet in Physics 30. You've done it in math class, but not in Physics 30. We're going to say it's 100 times 0.5, not times 10 to the 3.6, but just 0.5 to the 3.665. Everybody see what I'm doing there on the calculator? How I got that? What's your prediction here for n? Remember, that's bigger or smaller than 100? Bigger or smaller? Alex, what do you think? Bigger or smaller than 100? Well, smaller. Think about it. Like, we start with 100. It's decaying. We're going to end up with something that's something less than 100. So after 3.8 half-lives, 3.6 half-lives, we've only got about 8% left of what we started. At least that's what we're predicting. If we only have a couple of nuclei, well, then our prediction is probably not going to be very good. But if we've got a big sample of nuclei, then that prediction of 7.8% is probably going to be pretty close to where it actually ends up. Let's have you guys try a couple practice problems on page 814. I'll give you a few minutes to work on those. And then we'll take a look at them if we need to as a class here. One little thing that I want to point out before you start on it, though. Question 2, they're asking you for how much of this 100 milligram sample remains. They give an answer in percent. The answer should be in what? Milligrams, right? Same as the original amount is. But in the end, the number works out to be the same because my original amount was 100, just the same as it would have been for percent. Okay, so just the wrong units for our final answer there. Okay, give that a whirl, and then we'll take a look at it if we need to. Number 1. I'd love to go over number 1 with you guys. It says strontium-90 has a half-life of 29.1 years. What percent remains after 100 years? So we're going to say for number 1, the half-life, T1/2, or Lucas is calling it TX or TY or whatever the heck he wants to call it. Okay. It's the half-life. All right, sounds good. Whatever you want to write the symbol as, doesn't really matter. 29.1 years. The total time that's elapsed is 100 years. We want to find out how much remains. What percent remains? If we're talking about a percent, Nick, if we're talking about a percent, then odds are we're going to use what as our initial amount? Good. So we're going to say N0, once again in this question, is 100%. N is equal to N sub 0, 1/2 to the little n. Little n we got to find. But it's just like the total number of electrons is the total charge divided by the charge for 1 electron. The number of half-lives is the total time divided by the time for 1 half-life. 100 years divided by 29.1. What's that equal? 3.3-ish? 3.4? You got 3.436 half-lives. No units for that, just a number. So we got 100 times 1/2 to the 3.436. Let's do this on the calculator here. (100) times 0.5 times 10 to the, no, not times 10 to the, just to the exponent, 3.436. (9.24). So you can see that it doesn't take long. It doesn't take long at all for this to decay into about a tenth, about 10% of what it was. 3.5 half-lives, okay, to decay into 9.24%. Statistically, 9.24% of what it was. Now, the reality is it could be 9% or 10%. It could be off by a little bit. If we have a big enough sample size, it's going to be real close, though. All right, I got one more example to do with you here. This one's not in your book, so you're going to have to copy this one out, unfortunately. All right, let's write down some givens here. We got a half-life of carbon, 5,700 years. Look, the half-life of all the 20-some hundred odd radioactive isotopes that exist, they range anywhere from a fraction of a second to thousands or even millions of years. Okay, this seems like a long half-life, but there's a lot of elements with half-lives that are in that range of thousands of years. In that last question, we said it was about 3.5 half-lives. Well, that's not a lot of time if the half-life is 3 minutes. But if the half-life is 5,700 years, then 3.5 half-lives is a lot of time. The half-life of carbon-14 is 5,730 years. We start with 12.5 kilograms of carbon-14, and it decays into a final amount of 400 grams or 0.400 kilograms of carbon-14. We want to know how much time that takes, so we're looking for little t here, the amount of time that takes. Where do you want to start there? How do you want to solve this problem? Just give me something, throw something out there. I only have one equation with t in it, right? Go ahead. I'm sorry? Okay, so using that big equation? All right, so let's say n is equal to n sub 0, 1/2 to the little n. Now, that's not the equation with a little t in it. So in the end, once we get that n, we're going to have to go back to this equation, say t over t1/2, and just simply rearrange it for t, right? So let's get n, and then let's multiply it by the half-life of 5,730 years, and then we're good to go. We're done. Okay, let's get n. How do I rearrange that to solve for n? Who's taking Math 30 right now or took Math 30 last year? Who has not taken? Who's taking Math 30 next semester? Okay, a couple of you. So there's a few of you that have no idea what I'm talking about when I say logarithms, right? Okay, the good news is that's okay. There is a way to solve this using this mathematical technique that we call logarithms. But there is no question in Physics 30 where you must use logarithms. Okay, sometimes it's useful, but it's never necessary. We're going to solve this in two ways. We're going to solve it using logarithms first, for those of you that are comfortable with logs. For those of you that aren't comfortable with it, I'll give you a backup plan. Okay, another way to do it that you can solve not all your math problems with, but all the problems that we encounter in Physics 30 where we're not required to know logarithms. So how are we going to do this? Well, let's say n over n sub 0 is 1/2 to the little n. And let's say n is equal to log n over n0 over log 1/2 or 0.5. If that doesn't make sense to you, don't worry about it. If it does, go with it. We'll solve it this way. For those of you who this seems like a foreign concept to, we'll give you another way in just a moment to solve for this. So we got log of 0.4 over 12.5 over log of 0.5 there. Let's do that on the calculator here. Log 0.4 divided by 12.5. Let's divide that by log 0.5. I get 4.966. That's the number of half-lives, which I can take and plug into here. Multiply it by the half-life, 5,730 years. And we end up with a total time of 28,454. Or 2.85 times 10 to the 4 years. How many people are comfortable with that method? Good. Good. If you're not, like I said, it's okay. There's a backup to it. In fact, some of you that are comfortable with logarithms will still probably choose to use the backup method because you'll like that one better. The curriculum objective in Physics 30 in these problems says, exact wording here, it says that you need to perform simple, non-logarithmic half-life calculations. That doesn't mean you'll never see a problem where you can use logarithms, but what it does mean is that you'll never see a problem where you'll have to use logarithms. So what's the other way? Some of you looking at this, some of you that know about logarithms looking at this and saying, well, there's no other way. There's no other way to solve this problem. Well, there is. I'm going to use now what I call the divide by 2 method. I'm going to keep that first equation up there. Now I'm going to use a divide by 2 method to figure out what little n is. I'm going to make a little chart. After 0 half-lives, in other words, no time has gone by, I have 12.5 kilograms. After 1 half-life, I got half of that, right? Statistically, at least, I've got half of that. 6.25 kilograms. After 2 half-lives, I've got half of that, 3.125 kilograms. Just keep dividing by 2, hence the divide by 2 method. After 3 half-lives, I've got, I'm going to pull out the calculator for this one, 1.5625 kilograms. After 4 half-lives, I get 0.78125. And after 5 half-lives, I've got 0.390625 kilograms. I want to get down to 0.4. I'm real close to that. I'm real close to 0.4 kilograms here. So we're going to say here that little n is 5. 5, it's not quite 5, right? It was more like 4.9 half-lives. But we're close enough here to say that little n is equal to 5 half-lives. And we multiply that by 5,730 years. We're going to get a number that's slightly different than the last answer we got using logarithms, but it's going to be really close. What was the last one? 28,453, 28,650. Okay, I can tell you this. Either this question would not appear as a numeric response, it would be a multiple choice question, in which case you do it either way, you're going to see what's the answer, right? Even though they're slightly different, you'll be able to tell. Or it appears as a numeric response, and both answers will be keyed correct. Okay? You don't have to use logarithms ever in Physics 30, but you can, and you're not going to be penalized for knowing a little bit more math. Okay, how many people like the divide by, how many people like the log method better? How many people like the divide by 2 method better? Pretty much the people that have never heard of logarithms before, right? That's fine. Okay. You know what? I think I'll just give you a chance to work on some questions here now, okay? Your homework questions. I don't think I'll go to that next thing. Your homework is going to be worksheet number 25. There's I believe it's 12 questions on that worksheet. I want you to do the first 11. So all but the last question. Last question is a graphing question. You're not going to recognize that. Okay? Go right up to that.